Hello students. So today we are going to discuss about moment of force. Moment of force, which is also known as torque. Torque. The symbol for torque is torque. Okay, so let's understand what is this concept moment of force. So torque or moment of force, it is the rotational effect of force. It is the rotational effect of force. So force can produce different type of effect. Force can change the velocity, force can change the direction, force can change speed, force can stop a body, force can make a body move, force can do many other effects. Force can change the shape, force can change the size, all these, and this is the rotational effect. That means force can change the rotational speed or rotational velocity, you can say. That's the rotational effect. Okay, so how do we measure the rotational effect of force? So this is the term torque or moment of force. So the term torque or moment of force is a vector quantity and it is given as R cross F. Now let's understand here what it is. So this formula R cross F is about the torque about a point. Suppose for example this is a body, and with respect to a point, let's consider the point as O. Then this is the position vector. This object has got a position vector R vector, and there is a force acting on this body, and let us say the force acting is like in this manner. Some kind of force is acting on this. Or if I have to represent the force vector, I can represent force vector like this. So if force vector is acting on this body, right now the position of the body is this. This is the position of the body here. Let's say this point is point A. Of course, this is a object which is like a point mass. Object is a point mass. The body is present at point A. About the origin or about the point O, torque is calculated as R cross F. Now if you draw the R vector, you can extend this line, dotted line, okay, and you can split R along force or force along R, anything you can do. Let us draw the vector by joining the tail. This is R vector and this is F vector. I have joined the tail together. For vectors we can do that, and let's say the angle between them is theta. So what is the meaning of R cross F if you take the magnitude? That is R F sin theta. Okay, so there are two it's the same thing, but two idea that you can club F sin theta together. So if you resolve here F along this direction can be said as F parallel, and F perpendicular to this radius vector is F perpendicular. So F perpendicular is F sin theta, you know that, and F parallel is F cos theta. Already you know that, right? So here if I consider this F sin theta as F perpendicular, so I can write torque like this, right? So torque can be written like this. But there is another way to understand this. So let's understand this another way. If you consider this as R vector and this is the force vector. Okay, so now if I resolve, and this angle theta is the same, if I resolve R along force and R perpendicular to force, we can resolve in both manner. R parallel, again here R parallel is nothing but R cos theta, and R perpendicular is R sin theta. You know the resolution, right? So the same torque formula can also be written as R sin theta become R perpendicular, so you may write as R perpendicular into. So both way you can write this. Okay, So you can write it torque as R into F perpendicular or R perpendicular into any of this is okay. You can use any of this according to the given conditions in the question, right? And of course the direction of torque will be given by right hand thumb rule. All of you know that right hand thumb rule. Okay, so this is what it is torque. Now we can see some example on this, how to do the calculations. So take example of some forces acting. So there are some case studies we can do. Let us take case study. One case study is projectile motion. Projectile motion. So if you consider a body being projected with a velocity u, it is going in projectile motion, and consider that this is the ground. So when the body comes here, let us say body comes here, and you know this angle is theta, so you know the component is u cos theta and u sin theta. U cos theta component always remains same. At the maximum height, this vertical direction velocity is 0. You know this, right? Maximum height. Okay. So now this is the origin, let us say, and the body is right now at the maximum height. Suppose if I say find torque at A about O. What does this mean? When the body is at position A, what is the torque on this body? Okay, what is the torque on this body about O? We are calculating torque about O. So about O, we have to calculate. So what you do? What is the force? First of all, you need to think what is the force acting. Force already, you know, assume that no friction is there, only mg is acting. Now this is the mg, and you may join this will be like r vector, isn't it? R vector mg. So how to calculate torque? You have to take cross product. So either you can take r perpendicular into force or force into r perpendicular, but here I think to resolve r into r perpendicular, that is the best approach. This is r perpendicular. Okay, what is r perpendicular? R perpendicular is the distance of the point, distance of this point from the line of action. What is line of action? Line of action is the line of this force along which it is acting. This is line of action. So that torque you can calculate as this mg into r perpendicular. Of course, r perpendicular is this distance, which is range by 2. So mg into range by 2. Range formula you can substitute if you want. Right. So range is u square sine 2 theta by g, and here it is 2g. So this is what the torque will come. So it will come, and g can get cancelled, right? So m u square sine 2 theta by 2. Correct. Force into perpendicular, distance u square sine 2 theta by g. That is range divided by 2. So that's the torque we can calculate. Similarly, if they ask what is the torque at a different point, let us say the object has come here and almost near to the ground, it is going to touch it, but you know it's almost going to touch it. So here the force mg is acting like this, and the r perpendicular here is nothing but this distance is r only, range, right? That range is the perpendicular distance itself, isn't it? Because the line of action of the force, is this. R is anyway perpendicular to that only. So if you calculate torque here, at this point, this is the force into range, right? So it will be just 2 times. So it will be m u square sine 2 theta. Correct? This is how you can calculate. This is one example of case study in projectile motion. Similarly, you can consider the another case study for ladder. Case study number 2. It's a ladder. Sometime in the questions they ask that there is a ground here and this is a wall. So this is a wall, this is ground, and there is a ladder. So center of mass of the ladder is M. Total length is L. Okay. So you can show the forces acting on this. So forces acting here is mg. Assume that both the surfaces are rough. So if there is not rough, it will slide down. So friction will act here. Let us say friction 1. Here similarly it may go down. So friction should act upward. Normal should also be acting, right? So here normal is, let's say, N2. Here normal which is acting is N1. These are the forces acting on this rod, isn't it? Right? This is the forces acting. Now we want to calculate torque, or let us say condition for balance, or which is called rotational equilibrium. Consider it is in rotational equilibrium. Rotational equilibrium means net torque is 0. Net torque is 0. Just like rotational or just translational equilibrium means net force is 0. Rotational equilibrium means net torque is equal to 0. So here you can consider any point and try to calculate torque. You know, there are so many points are there, and if it is balanced about all the points. So let us consider this point as point A, and this point as point B, and this point as point C, or center of mass. So let's calculate torque about A. Of course, translational equilibrium means, as I told, translational equilibrium means net force is equal to 0. Of course, when net force is 0 means upward vertically forces are balanced, horizontally forces are balanced. That if you want to do, you can see the vertical forces that are acting on this body is downward is mg and upward is n1, right? And upward is n1, upward is also f2, correct? Because you can see here these forces which are acting here, this f2 is acting upward, and n1 is also acting upward, mg is acting downward. So these forces are balanced. Also, if you want, you can balance the other horizontal forces. Horizontal forces are f1 is acting towards left and n2 is acting towards right. So this is balanced. This is how forces can be balanced. Now balance torque about A. Torque about A, if you see the forces n1 and f1 is passing through that point, will not create any torque. Torque is only due to mg and n2 and f2. So mg, now let us just look about only mg. Mg is acting like this, and n2 is acting like this, and f2 is acting like this. F2 is acting like this. So about point A, if you are calculating, you need to know that this mg is going to produce like this type of torque, n2 is going to produce this type of torque, f2 is going to produce this type of torque. So you can clearly see that about point A, the torque produced by mg is clockwise, n2 is anti-clockwise, f2 is also anti-clockwise. So all these torques are balanced. That means torque due to anti-clockwise, torque due to clockwise, and torque due to anti-clockwise. They are balancing. So clockwise torque is due to mg into perpendicular distance. Perpendicular distance, you can see this is the perpendicular distance from the line of action. Line of action is this one, okay. This perpendicular distance is how much, and suppose this angle is theta, you take this as angle theta, so this distance is L by 2. L by 2 cos theta. L by 2 cos theta. Right side anticlockwise anticlockwise n2. N2 into what is this distance, the line of action. This is line of action. This line of action is separated by this vertical distance. Of course, this is same distance, which is L sin theta. Similarly, other force, which is F2 into this line of action is this one, total L cos theta. L cos theta. So like this, you can balance these forces and you can get equation. You can see, right? We have got equations. We have got this forces equation. So we can balance torque, we can balance force, and we can do so many calculations here can be done. Okay, so many calculations. Understood? So that's the key idea here. We can balance the torque. Okay. So I hope you have understood this. Thank you for your attention. Then we'll see further.